Hi, welcome to our YouTube teaching module on Beta-Lactam Antibiotics. In this session, we will explore the fundamentals and the most recent development in this crucial class of antibiotics. Beta-lactams have been the cornerstone of bacterial infection treatment for decades and continue to evolve as resistant strains keeps to evolve. Whether you're a student or a pharmacist or even a healthcare professional, this session is designed to bring you up to date with both the basics and innovations in beta-lactam chemistry and pharmacology. Let's get started. Beta-lactam, as we know, it is widely used over the world since the invention of the first clinical trials that happened in 1941 by Chen and Florey. It has evolved. We have so many semi-synthetic penicillins. They are divided into several classes, but all of them have got the beta-lactam ring structure in them. And then this is what we call the beta-lactam ring. I'll tell you why they are called beta-lactam. First of all, a lactam is a cyclic amide, and a beta-lactam because the nitrogen of the amide is attached to the beta carbon of the carbonyl group. This is the alpha carbon, this is the beta carbon. So this nitrogen is attached here. That's why it's called the beta-lactam. Okay, so we are going to go to the next thing. Well, I'm not sure you are really interested much in this, but you can pause and then have a look. Starting from the discovery of Alexander Fleming in 1928 on a serendipitous discovery, to now that we've got a whole lot of novel beta-lactamase inhibitors like the avibactam, dulobactam, and all that. So we are going to talk about what is most recent, and now before you go on, I want to ask you a question. Why are beta-lactam antibiotics called beta-lactam? Okay, you can pause and answer this question. If you can't, rewind and then go back to the previous slide. How do they function? What do they target? So these organisms attack us, but the penicillins actually select something in them that we don't have and attack, and that thing is the cell wall. Humans don't have cell walls, and the cell wall is made up of what we call is a polymer, a carbohydrate that is called peptidoglycan, and the peptidoglycan is made up of alternating unit of NAGA NAMA, as we get to see later. Now the cross-linking of this NAMA, different strands of NAMA, is what creates the peptidoglycan. That this is what creates the cell wall, and if this is inhibited or disrupted, the synthesis of peptidoglycan does not happen, and the Turgor pressure caused by osmotic pressure differences between the inside and outside of the cell leads to cell lysis. So the cross-linking is actually catalyzed by an enzyme transpeptidase called the penicillin binding protein. So like I said earlier, the beta-lactam is a carbohydrate composed of alternating units of NAMA and NAGA. NAMA is N-acetyl muramic acid, and NAGA is N-acetyl glucosamine. The linking happens between the side chain, then the L-lysine residue of the peptide side chain of NAMA, and the dialanine terminal link on the neighboring NAMA link unit. So, but this L-lysine is mostly in the gram negative. In the gram positive, you have the mesodiamino pimelic acid. It replaces this. So this is the structure of N-acetyl glucosamine. You look at this and look at this. If you hydrolyze off the acetic acid moiety here, then you have back the glucosamine. Every other thing is the same. And I already mentioned the reason. Explaining the reason why the beta-lactams are safe is because humans do not have peptidoglycan. So as a result, beta-lactams are generally well tolerated. Often the only problem we have is gastrointestinal disturbance. Personally, if I have any reason to take either augmentin, or amoxicillin only, or ampicillin, I go to the toilet. And when you go to the toilet frequently, the stooling is quite nice because it doesn't waste time. It goes and you get out of the bathroom, the toilet actually. Well, about 10% may have some life-threatening anaphylaxis or some minor allergy, like rashes on the body. So you have to be careful. If you notice things that you don't understand, then you have to be careful with the use of Beta-lactam antibiotics like the cephalosporins, the penicillins, and carbapenems, and all that. So the carbapenems may also cause seizures at high doses, but nobody wants you to take high doses. So if it's resistance is resistance, there's no point abusing it, except people who want just to kill themselves. And in patients who have renal functions, renal functions that are not good. So I've already mentioned that the gram-positive use mesodiamino acid for their own cross-linking, the gram-positives. Now, looking at this, I was talking about the linking. The DLR here is the L-lysine, but in gram-positive, in some, you have mesodiamino pimelic acid here. Okay, and this cross-linking is, especially in the gram-positive, is facilitated through beta-glycine unit, and the transpeptide, the penicillin binding protein, is what catalyzes this cross-linking. Look at this and make sure that you know that this is happening where it's happening. Okay, this is a growing peptidoglycan moiety. Glycan is carbohydrate. I've talked about this, and so I have to talk about the transpeptides and the role they play. they have to be able to recognize the DLR during the cross-linking. And what it means is that if you have anything that resembles the D-alanine moiety, that you can actually bind on it. So interference with the binding, or by the interference with the recognition, disrupt the cell wall synthesis. Now, because the beta-lactams look like the D-alanine moiety, they can stand in the place of D-alanine and D-alanine, so they will deceive the penicillin binding protein, disrupting the cross-linking process, and that's how they kill the organism, because they disrupt the cell wall synthesis. So what I'm talking about, you're looking at penicillin nucleus, and you're looking at D-alanine nucleus. So look at that, start from here down. Now, for penicillin to work, it must have this, and that tells you something about the electron distribution of the receptor, you know, on the enzyme, on the active side of the enzyme. So normally, if you know what drug development is about, we consider three things. We consider the hydrophile lipophile balance, to make sure it can pass through the membranes, both the membrane and the aqueous surrounding, to get to the point, the target receptor, or where it's going to act. We also make sure that it's not too big. If it's too heavy, probably won't get close enough to bind. And then you also make sure that the electron distribution is such that it is able to attach to bind to the receptor that we are targeting. And the electron distribution here, because you have similar molecules along the line, so there's no reason why it will say no to this. So it's easy, you can say, okay, it goes for it, but eventually it binds to the serine OH unit irreversibly, and then deactivates the enzyme. And then when it's activated, the enzyme, as many as there are there in the system, it reduces the activity of the enzyme, and then the synthesis of the peptidoglycan, leading to lysis of the cells. And of course, the body defense system takes care of the rest. So this is why beta-lactams are effective. And that's why if this is broken, if you have any structural activity relationship, if there's any breakage here, it loses activity, because the PBP will not recognize it anymore. Now, recognizing it is not just, there's a reason why it binds irreversibly. There's a reason why it binds irreversibly to the enzyme, and the reason is this: the bond that it forms with the enzyme serine OH subunit is the bond is irreversible. It's broken. It breaks the amide bond, and there are things that make that happen. Remember, amides are ordinarily not very reactive. So if you look at an amide like this, let's see what we can do with this. So I know. So let me see. You have this. This is N. You have this R, and you have this as O, You have R, so this is R1, this is R2, and this is R3. You have this. So this guy here ordinarily can form resonance structures. Okay, so this one structure and the second structure will look like this. So this is going to give you this is a reversible. I have N here. You got this. You have that just like the other one. And then you have R1, R3. And then R2. Then you have R1 here. You have oh sorry, that doesn't work. This is what we want to do. So we have this, and then this is negatively charged, and these two are they're interchangeable, and you can find both of them in the solution at any particular time. But that is not possible with our the beta-lactam ring. It's not possible here for a couple of reasons. First of all, because of this 4-5 fused 4-5 ring prevents the nitrogen from being planar, and as a result, there's no resonance stabilization. So this guy here cannot. Sorry, that drawing is wrong. What I wanted to do was to drop these two and this. So this lone pair of electron cannot go like it did here, and because it cannot do that, this is exposed to a nucleophilic attack. So, and two, the angle here, because this is an sp3 hybridized, the angle here is supposed to be 109.5, but it's not. This is 90 degrees, and there's an angle strain here, and there's also a problem of this is not planar, and it's going to have a problem, So all these things come together to make sure that this bond here is very reactive. And now, to the reason why the reaction proceeds and is not reversible. It's not reversible because when the beta-lactam acylate the hydroxyl group, of the serine residue, as I mentioned, the PB of the residue of the PB active site, it is not a reversible reaction. And why is it not reversible? It's not reversible because there's an oxanion hole, and that oxanion hole is a region in the active site of the enzyme, and it stabilizes the trihydral intermediate by forming hydrogen bond with the negatively charged oxygen atom, reducing the transition energy. So if it reduces that transition state energy, the reaction, the tetrahedral intermediate is stable enough, and allows the nitrogen here to pick up a hydrogen from the medium, and then will not have any need for any other person. This guy here, the girlfriend has rejected him because he was not paying attention, and then he decided to get another girlfriend. And that's exactly what happens, and that what stabilizes it. So you have an irreversible reaction, the bond is broken, the enzyme has been sequestrated, it cannot do anything, has prevented from building. So this is very, very important for the success of the mission or the beta-lactam mission. Okay, so I'll ask you this question: how does PBP attack penicillin, or how the same question, how does penicillin inactivate PBP? I've explained it a bit, but let's go. So just to show what I've explained, the hydroxy moiety attacks the imide and forms a tetrahedral intermediate. Now, this, what you're looking at right now, the serine so the serine subunit, the serine OH, or the hydroxy unit, comes here, attacks, and then of course when it attaches, you are supposed to have 5 bonds to carbon, which is not possible. You can only have 4, so it leads to bond breakage as it is now. So when that happens, this is the tetrahedral intermediate we'll be talking about. So this tetrahedral intermediate, the oxyanion site forms a hydrogen bond with this hydrogen, making it stable, and then breaking this bond. And when this bond is broken, hydrogen likes to pick another girlfriend, the hydrogen from the medium, and that leads to the formation of something like this. This remains eternally bound to the beta-lactam. Well, the beta-lactam is no longer useful, at least by has done its work by stopping, it has stopped the synthesis of peptidoglycan, the peptidoglycan, which is the major backbone of the cell wall, or major component of the cell wall. So the beta-lactam can easily penetrate gram-negative, but the outer cell membrane of gram-negatives prevent the absorption of the drug. That explains to you why the earlier beta-lactams do not have activity against the gram-negative. But with time, these things change because of engineering, synthesis. Beta-lactam can be modified to make use of import porins in the cell. Now, the import porins are polar. So if you can make the beta-lactams utilize that by making it a bit more polar, but I've talked about it doesn't have activity against humans, but any bacteria which lacks peptidoglycan in the cell wall will not be affected by beta-lactams, and that's the truth. But the beta-lactam will find a way to get in there. You can, in fact, recent innovations is taking care of that, as we'll see later. So we already know the different mechanisms of resistance, efflux pump, inactivations, but at the moment there are new ones. Those old ones are gone. It's kind of, they have been taken care of, but there are new ones that, these organisms just want to survive, but they want to survive at your expense. So they find a way to resist, is adaptation to resist to resist you and resist the drugs or your ammunition. When one Surgeon General said after the invention of penicillin that the war is over, or the war was just starting. So extended spectrum beta-lactamases, the enzymes that inactivate, or we have the normal beta-lactamases, you have the metallo-beta-lactamase enzymes, we have the carbapenimases, you can imagine that. Now the carbapenimases, like the Klebsiella pneumonia carbapenimases, or the New Delhi metallo enzymes, or the Oxa 48, these enzymes are capable of hydrolyzing a wide range of beta-lactams, including carbapenims. And these are the reasons why we are having things like in 2019, the CDC talked about the urgent threats. These ones in this group are the urgent threats. We have the serious threats, and you have the concerning threats, and we are the ones to watching groups. All of them, they're important, but when it gets to the ones that resist the carbapenims, that resist the carbapenims, then you have a problem. And at the point it looks like we are running out of ammunitions against these organisms. It is still like that, it's still urgent as it is right now. People are dying from just infection of these kinds of organisms. So I'm not sure you are very much interested in the molecular biology of all this, but we'll keep mentioning them in case you want to know. So the Oxa 48 is a class D. You have the class C, you have the class A, you have the class B. It's the different types of them. So we talked about the resistance. The urgent ones, the carbapenem resistant and Enterobacteriaceae, methicillin resistant, and all that. And we have the serious ones, and we have the concerning. You can look at them as they are. And because of this, an innovation, the Trojan horse antibiotic was brought in. And we know the story of the Trojan horse, the Greek myth, where the horse loaded with soldiers was given as a gift. It's just like a Greek gift. Basically, the thing that was, taught about by scientists, and good thing, we have achieved something through this. I think in 2019, a drug was approved and is currently in the market. So this is achieved by linking an antibiotic to siderophore, a molecule that bacteria use to scavenge iron, essentially tricking the bacteria into taking up the antibiotic. That's how it looks like, the Greek gift thing. So because the bacteria needs iron, and they use siderophore to scavenge iron from the system. So if you attach anything to iron, they will take it in. And it's a way of bypassing all the resistant mechanisms of the antibiotic, of the microorganisms, whether gram-positive or gram-negative. So recent modifications include the development of siderophore cephalosporin, and it's called cefiderocol. And that activity transports across bacterial membranes, and newer inhibitors like avibactam, relibactam, and Beta-Lactam. So we have new inhibitors, but this particular guy is not an inhibitor of any bacterial cell wall or bacterial enzyme. So it just helps cephalosporins to go through the membrane, avoiding the efflux. In fact, when the siderophore is going in with the cephalosporin, the organism shuts down all its efflux and resistant mechanisms to allow it because it sees it as food. So that's. But these other ones, we have newer inhibitors like this avibactam, the relibactam and verbibactam. We're going to talk about them and how they're used. So we talked about the different classes. We already mentioned them. The only one we've not talked about is the monobactam and the penicillin, cephalosporin, carbapenems, and monobactams. So here we have the penicillins, and I've used this structure already to explain something earlier on. This is a typical penicillin. So beta-lactam antibiotics can be modified at various positions to improve their ability. So I talked about, at the beginning, at the second slide, I talked about from the time, I think in 1950s, it was possible to isolate the cis APA, and then with that, the floats or the doors were opened up for semisynthesis, making some derivatives of penicillin or beta-lactam antibiotics. So to be able to administer them orally to survive acidic conditions, be tolerated by the patient, penetrate the outer membrane of gram-negative bacteria, prevent hydrolysis by beta-lactamases, and isolate the BPPs of the resistant species. So a whole lot of modifications were made possible with that discovery, or the groundbreaking discovery kind of. This is not complete, but is a question, and what I want to ask is, do you know the structure of penicillin that was obtained directly from mold? In other words, I'm asking you for the structure of penicillin G, and that is the natural penicillin, the naturally occurring penicillin G. So this is the one. My image here is blocking this. This is COOH. You would have seen it from the other one. And this is not really active because it cannot survive the acidic condition of the heart. Of the gut, sorry, not heart. That's the condition of the gut. I am not even sure. Okay, penicillin G may be still used for syphilis and maybe some kind of gonorrhea, but apart from that, I don't know what other indication that is easily used for. So that is the structure I was asking you of in the previous slide. Now, one of the problems it has itself is the problem of neighboring group participation. That's how it is destroyed on its own. So, a neighboring group participation is the involvement of a nearby nucleophilic substituents in a substitution process. And the thing is that for you to call it a neighboring group participation, the nucleophilic group must be a part of the molecule. And so the nucleophilic center can be a lone pair of electron in an atom, like a nitrogen lone pair, as it's very close to the carbonyl group. electron in sigma or pi bond near to the reaction center, has to be near to the reaction center, but it cannot be conjugated with the center that is going to be attacked. So I've already mentioned this. And I've shown you what is the tetrahedral intermediate already. But we're going to look at the process of numeric growth participation. So this here this is cut off, but this is supposed to be there somewhere here. So what we have here is there's a lone pair of electron here, like we mentioned earlier on, and that lone pair of electron goes here, and then this attacks. Remember when I said that because there's no possibility of resonance, because this is not planar, and this in my idea is not resonance stabilized. This guy is starved of electrons, so it is prone to nucleophilic attacks. So the nucleophile attacks right this point, and when it attacks this point, you have something like this. It breaks up and have a tetrahedral intermediate like this one, and then because you're in acidic condition, you have hydrogen ions that can easily be picked up from the system, to satisfy the valence requirement of the nitrogen here, and then we are good. And then you have this. It looks to something like the mechanism of action against or that makes it stop peptidoglycan synthesis. If you remember what we discussed, so it's basically the same thing. It goes back here, and then that's exactly the same thing. So it breaks it up, and because if there was nothing like this, maybe this cannot happen. But because in ionic, in acidic medium, where we have a lot of hydrogen ion, this happens. So if you don't have hydrogen ion, so it cannot happen in alkaline surrounding. So that's why it doesn't survive acidic medium. So this is not active. Penicillin V is produced when the phenoxy, you see here, instead of just this attached, this is a phenyl group, the benzene moiety or benzene moiety. Instead of just benzene moiety attaching here, having a benzyl, because you have a CH2 here, then you have an oxygen here which is electronegative and reduces the nucleophilic capability of this unit here. So if you reduce the nucleophilicity of the carbonyl group, making penicillin V acid stable and orally viable. So that's why I think penicillin V you can even chew it. It's going to be very big. All right, and it still works properly. So these are some of the modifications we talked about to make it orally available, to make it resistant to. However, this is not resistant to penicillinase enzyme. So talking about commercial production, all commercially available beta-lactams are initially produced through the fermentation of bacteria. And bacteria assemble the penicillin molecule from L-amino adipic acid, L-valine, and L-cysteine in 3-step using ACV synthase, APN synthase, and acyltransferase. Well, we use modern technology to increase the expression, of the genes that code for these three, allowing for much greater yield. So look at the L-amino adipic acid, L-cysteine, L-valine. So this is a basic synthesis in a fermentation medium. So the ester side chain here of the penicillin molecule can be cleaved using enzyme or chemical methods to produce cis-APA, which can further be used to produce semi-synthetic penicillin. I've talked about it. Now, 7% of penicillin produced is modified in this manner. Okay. So when you cleave this off, you get this. Now, we talked about producing penicillins that are resistant to penicillin S. So this one of them by attaching bulky side chains. And what it basically does is that it physically keeps the penicillin S, the beta-lactams away from this active side. And by that way, they are able to resist and still attack, the PBP proteins. These things are huge. So with it, the penicillin S enzymes cannot get close enough. However, the PBP can still recognize them. Okay, they can still recognize them. So penicillins the anti-staphylococcal, these lactamases are prevalent in Staph aureus and Staph epidermidis, render them resistant to penicillin G and V. Okay, so when we have things like the methicillin, which has those bulky sides, you have the oxacillins, you have the nafcillins and all that. But there are still some of them, even though they are resistant to penicillin, some of them are still not good enough, because at the moment they're not as effective as they used to be. Bacteria are all very intelligent. They're intelligent beings. So that's why, as they're evolving at the beginning, I said there have a new form of them come up. When you know that this, okay, it happens, it works for a while, and then we change it, and then these guys change tactics, we also change tactics. And that's what science has been doing, research has been doing that. So let's see. Like I said, methicillin sensitive has been improved upon by adding electron withdrawing groups, as was done in penicillin V, resulting in drugs such as oxacillin and nafcillin. And due to the bulky side chain, all of these staphylococcal drugs have difficulty penetrating the cell membrane and are less effective than other penicillins. So that's the problem we have with them. Because they are very huge, I mentioned there are 3 things you look at when you're designing a drug: whether they will be able to get through the cell membrane, and this one is having that problem now. They're not able to get through the cell membrane, or are not as efficacious as the other ones. Maybe they're good. Well, you get them into the gut, they might have local effect, but not as good parenterally, except you administer them through the IV. Parenterally. Okay. So you have the oxacillin now. This has oxygen started here, and here with this unit, this is an 5-methyl that is here. It reduces. This is very huge, actually, as a matter of fact. So it's able to prevent the access of beta-lactamases, but it also reduces the nucleophilicity of this unit. And by reducing the nucleophilicity of this unit, the cytidamide unit, then it can be acid stable. It can also go through, like I said earlier on, it go through the gut, but because of the bulky nature, getting through the membranes becomes a problem. And it's also not only that it's bulky, it also has it is a bit more hydrophilic than the ordinary penicillin G. This is a methicillin we are talking about, and this one is totally not acid stable, so it's very acid sensitive. Now, to take care of some of these problems, so to increase the range of activities of the penicillin, I talked about this, the amino penicillins like ampicillin and amoxicillin were modified to have more hydrophilic groups, allowing the drug to penetrate gram-negative bacteria via the porins. Okay, so these guys are more hydrophilic, and the porins are polar, filled with aqueous liquid, if I should use that. So the porin is a channel to proteins. So, and the proteins are actually polar. Now, the ampicillin, when the R here is a benzene ring, then you have ampicillin. But if the R is hydroxybenzene, then you have amoxicillin. So now I have the extended spectrum penicillins, and they're similar to amino penicillin in structure, but have either a carboxylic group or urea group instead of the amine. So we're looking at that's the urea unit or the carboxylic unit here. So these ones are extended spectrum, or what do you mean by extended spectrum? That they are able to they have activity against a wider range of organisms. Okay. So like the aminopenicillins, the extended spectrum drugs have an increased activity against gram-negative. I just mentioned that, and these drugs also have difficulty, but they are not as susceptible to beta-lactamases. So let's look at the classic beta-lactamase inhibitors, and they are the clavulanic acid. The one you have the augmentin. Augmentin is amoxicillin plus clavulanic acid. You have the sulbactam, like the onacin, ampicillin plus sulbactam. And you have the zosine piperacillin plus tazobactam. And then you have the mitin, which is ticagrelin plus clavulanate. But these guys are not all doing great anymore. Augmentin is still good, for a lot of respiratory tract infection and stuff, that upper and lower. But all of them are beta-lactam derived, and they're all obtained from streptomyces fermentation. I'm talking about the three. But we have newer ones, and they are not effective against AMP-C and carbapenemase enzymes or beta-lactamases. So we're having issues right now. So formerly effective augmentin is no longer effective at all against some resistance genes. So let's look at some new beta-lactamase inhibitors. We have the Beta-Lactam, but this one is not derived from beta-lactam. It's a non-beta-lactam diazobicyclic octane. So it's combined with ceftazidime and I remember using this. Dispensing this a lot. I'm talking about the ceftazidime called Fortune. I think it's GlaxoSmithKline. That used to be a very good, immediately, especially on kids, pediatrics, when you have issues and you expect there's kind of a blood infection. The pediatricians just did boom. After the next minute, the child is okay. But you see what we're talking about. These things are being ineffective now, but they're very expensive as well, if not that. So when you combine it with Avibactam, one of the new inhibitors, it's about 10 years old, was approved in 2015. It's totally good now, something you can look at, and the name is Avicaz. So if you're having problem treating something that you think ceftazidime could treat before, please look for Avicaz. Or I think it might still be the only version of it available. So Avibactam is reversible. Avibactam does not inhibit class B MBLs or the New Delhi ones, and is not active against Acinetobacter class D inhibit beta-lactamases. The Klebsiella pneumonia carbapenemases that produce carbapenemase resistant enterobacterialis and other resistant gram-negatives. So first line option for KPC, producing enterobacterialis and oxidase producers. So we have a new agent right here. This is a new agent. It has been in use for about 10 years now. So we have the Avibactam. This is not a DBO. This one is a boronic acid inhibitor, boronic acid derived inhibitor. You can see the structure right here, quite different. And its unique structure and selectivity potent against class A serine carbapenemases, especially KPC. So Avibactam is paired with meropenem in Vabomere, approved in 2017, so less than 10 years. So the combo is effective against KPC producing CRE, ineffective against strains that has MBL, like example the New Delhi metallo-beta-lactamase enzymes. Well, it has superior outcomes to colistin-based therapy for CRE, and colistin is a bit toxic. So with this, or at least you have something that is you can rely on. We have the Beta-Lactam, which is a DBO, structurally related to Avibactam, class A, combined with imipenem as well as lastine. You have Ricabrio. This was approved in 2019. So these are the new things some of us might not know about, and we're bringing this to you for your information. It's effective against the KPCs, AMP-C producing gram-negatives, and also Pseudomonas that have AMP-C, beta-lactamase, and their flux. This is really a very important drug. and it can actually take care of a lot of things. We just hope that our friends, the clinicians, should not abuse it. Should be the drug of last choice, and not the first choice. That should be the smaller one should be tested first before you go for this. Then we have the Beta-Lactam, and this is another DBO. This is when it's combined with, is paired with Sulbactam. So here Sulbactam acts as the antibiotic. The Sulbactam acts as the antibiotic, and the Beta-Lactam acts as the inhibitor. So now we have the last one, which has not been approved anyway. So the impactor efflux is not approved in the US, but in some regions they are approved. They are good against the MBLs. Some people, instead of waiting for it to be approved, are using it. So that is the Avibacter, the one we mentioned earlier. Then you combine it with azithromycin, and that takes care of it. So you have ceftazidime, avibactam, you have avibactam, you have ceftazidime, and then you add azithromycin to it. So this is very good against life-threatening NDM producing infections. Okay. So look at what we have mentioned before, exactly what I've listed right here for you. We have the ceftalozone, tazobactam, zebata, protein 14, ceftazidime, avibactam, efficacy 215, meropenem, verbomir 217, imipenem, calcium, we have recarbra 219. Then the cefiderocol, this is the Trojan horse antibiotic. It was approved in 2019. The Sulbactam, Beta-Lactam, the Zactro was 2023. This guy is still new. It's on phase 3 trial. And then azithromycin is the last we discussed, which is still being, the approval is being considered. It will come in very soon. Everything, if it passes everything. In the US I'm talking about, but in some other regions, this approval has been granted. Okay, so we're going to stop here. It's supposed to be an hour lecture, and we're going to take the cephalosporins next time. If you have any comments, drop it. Any questions, drop it in the comment section, and then we'll deal with it. Thank you very much for watching.